All right, so here is that theorem that I was just talking about, okay? And actually, number one is something that we've talked about before, right? That the limit as x goes to infinity of some number divided by x to the r power, okay? If you have a positive rational number, that's going to be 0. And that really makes sense, right? Because basically, if you had infinity to a positive number, it would just be really, really big. And so we've talked about this before, that if you have some number divided by something really big, right, that actually equals 0. And the same thing is true here, that if I do the limit as x goes to infinity, a negative infinity, that the same thing will happen, right? It will get closer and closer to 0. Okay? And then, okay, and maybe as a good example, I could do this for you. So this is still for number 1. If we had an example of y equals 1 over x squared, okay, and for a second, let's just think graphically, right, that function looks kind of like the volcano function at x equals 0. There's a vertical asymptote there. But it turns out, right, the closer or the farther you get out here, the right end behavior, right, the closer that gets to 0, and the left end behavior, right, the y values are also getting closer and closer to the x-axis. And so if we think about it algebraically, right, the limit as x goes to infinity of 1 over x squared, that would be like 1 over infinity squared, which would, again, be really, really big, okay, and that makes sense that that would be 0. Same idea here. If I say the limit as x goes to negative infinity, I'm dividing by this negative number, negative really big number, and I'm squaring it, so again, it's 1 over really, really big, right, and it would be positive because I'm squaring it, and that, again, would equal 0. Okay, we've actually talked about the other part of this too, number 2, right? The limit as x goes to negative infinity of e to the x would be 0. Let's think about that graphically for a second, right? If I think about the e to the x graph, it looks like this, right? So the closer I get to the left-hand side of this graph, right, the closer to 0 that's actually getting. What would we say about right end behavior here? We would say that it doesn't exist, right, because it's going to continue to increase. It's never going to an actual number, right? So this is actually a good example where we wouldn't be able to say, right, so the limit as x goes to negative infinity of e to the x equals 0, but the limit as x goes to infinity for e to the x would be dne, right, because it would continue to increase without bounds. Another optional answer, right, would be infinity, but infinity is not actually a number. Okay, the second part of this is the limit as x goes to infinity for e to the negative x equals 0, and that makes sense. We talked about this. What does this graph look like? Okay, and this is that version of it, right? And so it should make sense to you the farther out to the right, or the limit as x goes to infinity of e to the negative x, that should equal 0. Also makes sense if you think about this as the limit as x goes to infinity. If I rewrite e to the negative x as 1 over e to the x, do you see that this is going to be a situation where you're 1 over something really, really big? And so that makes sense that this would equal 0. Okay? All right, so those two things are pretty important in terms of our future work. Okay, so I'm going to end this. Make the next one in a second.